Um, I think I'm gonna start. Just one quick question. Who here has used Go for less than a year? Okay, nice. It's always nice to see the community growing. A little bit of introduction, if this thing can get to work. Okay. I've been using Go since 2015. I currently work in security announcement for the web at Google, and I try to use Go as much as possible for everything, even if it doesn't really make sense. I don't suggest you to do so, but it's a fun exercise. I've always been interested in parallel programming all my life, and I come from a background of C# and Python, and if any one of you has tried to do parallel programming in Python, you know what pain I've been through. And I'm sorry for you if you try that yourself. So, a little bit of agenda. Today I'm going to talk about contention. Contention is an overloaded term, so I'm going to introduce what it is, how to measure it, how to reduce it, and how to be surprised by it and not being able to actually address it. Contention is a competition between different processes to acquire resources. Doesn't mean if it is for reading or for writing. As long as you have a shared state between processes or a concurrent thread of execution, you have contention. Usually, it doesn't really matter. But with Go, we are used to spawn Go routines as hell. We just create these huge heap of Go routines because they're simple, they're easy, and if you think about HTTP server, you spawn one Go routine per incoming request, you really don't care. So initially, you're going to go fast, and you realize that Go makes it easy to use all the cores of your machines, and you're happy with that. And after a while, you realize you need to go faster, so you start inspecting your code. So let's do it like scientists are supposed to. Let's measure it. I think that Go is one of the best languages, tool-wise, full stop, not just for performance tuning. I think we are lucky on the tools, on the standard library, on the ecosystem, and pprof is one good example of it because it gives you a lot of information with one of the worst possible UIs you can possibly use. It's getting better in the latest years, but it's still very close to the original Unix, like do one thing, do it well, make it very hard to read. So those are actual screenshots of the output of pprof, and if you have your code and you just run your benchmarks and you add one more flag, the CPU profile, that is going to create a file. You can then use that file with a Go tool pprof. You can also pass the executable. It used to be mandatory, is now optional, and you just pass that file. If you now type web, a new whole world opens in front of you because it's going to show you a lot of information. Today I'm going to go to talk about contention, so let's take a look at it. This is a very simple example of code. I have an A variable that I declared outside, and I spawn many Go routines, one per core in this case, and I just acquire a mutex, increment the variable, release the mutex. I just want to give you a simple example. Usually there is more work, not just an increment, but this is what Go programs usually look like. You just acquire mutex, do your work, and write to the shared state. This is one bit of pprof that tells me that in my function, I spent 0.04 seconds doing stuff and 2.4 seconds doing something else. If you read this kind of pprof, you're usually wondering, why? What am I doing? Why? And so let's take a look at the global part of this. This tells me that basically my entire time was spent on the lock contention. The output of pprof shows you bigger box, the most time was spent in the function, which is useful if you just want to give it a bird view. It's a little bit harder to read the squiggly lines in there, so it also has a command line version. And for those who fancy flame graphs, it can also give you a flame graph in which you can click and it expands the block you click on. This makes it very easy to understand what is going on. In this case, for example, I spent a lot of time in sync runtime do spin. I will not get too much in details with how the mutex work in Go, but I'll just tell you that for the first attempt at acquiring a mutex, it will just go, try to get it. Did I get it? No. Okay, let's retry. Maybe a couple more times. Did I get it? Still no. Okay, maybe it's time to actually stop trying and just yield and tell the scheduler, just let me know when this is ready. So I burned a lot of CPU just doing that spin. And I wanted, this is taken, it is actually a more simple example of an actual code that I had to debug. And I wanted to know where this was happening, because I had a lot of mutexes around in my code, and I wanted to know which one was the problem. And so if you run pprof with mutex profile, it tells you the line. Tells you exactly, this is where you spent the most time waiting. And this is very easy to read. And you can expose this in every editor, but even the web view just gives you the code highlighted in this way. So I knew where to go and optimize. Sometimes this is still not enough, so you need to know more. And to do that, there is another tool, trace. Trace is even better on the point of information that it gives you, and even worse at being used and understood. So this is a real challenge. I think I spent several hours trying to understand everything I could get from trace. I'm still confident I'm missing most of it, but it gives you some information. I mean, some things are easy to surface, and I'm going to show an example later. If you want to collect traces, you can just test with different flags. One more thing that you can do is, and that I always suggest, is do not just run your benchmark and read those benchmarks and trying to understand where to optimize, because benchmarks are artificial. One nice thing about pprof is that it can run in production. If you import pprof and you don't read the traces, it doesn't cost basically anything. So you can just run it in prod, and when you see that your latency is, for example, going up, just collect one trace. So you have actual data to work with, not just artificial benchmarks. And once you do that, it shows you this page with a lot of links, no CSS, no style, just links in plain HTML. And let's click, for example, on the regions part, if you have trace regions. This is what tells me I have 4 Go routines, because I have 4 cores and I spawned just 4. And it tells me that out of those 4, 3 took roughly 10 milliseconds, 1 took 6 milliseconds, 0.6, actually 6. One thing that I really suggest to use this for is tail latency. Since you see all the Go routines that got into this zone, sometimes you will get like 1,000 Go routines just took a little bit, and 1 took seconds. That is the one you're interested in, because your users are never gonna care if your application is fast. They just use it. But when that user is hit by that 2 seconds latency, you're losing money. Your users are not gonna be happy, and since I am my main user, I'm going to be annoyed. So that is very useful. One thing, one column that you can use to just take a look at your mutexes and see where you're wasting time is that sync.Locker. In this case, out of 11 milliseconds, roughly, I spent 7 executing my stuff, and a lot of time in the scheduler waiting, and a lot of time blocking on a mutex. So this gave me information. If you don't have time to add traces to your code, because regions need to be added manually, you can always click on the Go routines link, and it gives you a similar view. It's less granular, but still gives you a little bit of information that you can start working with. If you click on the trace tab instead, you end up with a UI that roughly looks like this. You can't change the colors, so if you're colorblind. So what you see above is the number of Go routines. Then you have the heap, and the amount of threads that you actually spawned. And here, there are the processes, the things that you're actually doing. And if you're contending a lot on a mutex, you're going to realize that those blocks are never too contiguous. You just execute a little bit here, a little bit there, a little bit there, but you're not parallelizing, really. You don't have continuous lines. You just have blocks here and there. And that's where you realize, okay, I spent too much time waiting. But be aware, the uncertainty principle is still true even for computer science. You cannot measure too precisely and still have a reliable measure. And I know that very well because while I was preparing this talk and while I was doing my benchmarks, I realized that I was just measuring the trace library. And I mean, it's pretty good, it's written very well and everything, but that was not exactly the point of my code. So I decided to just remove some traces here and there. Just be aware of that. Before I go on and explain you how to fix contention, because now we know how to measure it, I would like to please ask you to not do what I'm about to tell you unless you have to. What I'm about to tell you are tricks and ways you have to go faster, but that doesn't mean you have to go faster. I hate it when people remove everything they can just to go faster for the sake of it. Make sure that this is your bottleneck. In my case, it was. And if, for example, you're writing a deeply concurrently accessible cache, you're going to need this kind of stuff. But you have a service that is split across 10 microservices that every time need to communicate with each other. You're going to hit the network basically at every request. That is so much slower than acquiring a mutex that you're probably not going to care. This is what a normal Go program looks like. You have producers, you have a channel or a mutex protecting collection, and you have consumers. This is how I usually look at it, and it makes it easy to read, and I love that about Go, because you have concurrency and you almost not even realize it. It's the job of the scheduler to serialize those kind of operations and make them usable. This is how you see it, this is how your hardware sees it. There is a bottleneck on both sides trying to access that shared content state. And as much as we love readable code, that's not always feasible. If you think about, okay, let's switch from a channel to a mutex because maybe I can go a little bit faster, you can. I mean, no one is preventing you from doing that, but I just let you know that channel is just a struct with a mutex on it. So, I mean, yes, you can try to go faster. You will actually realize it's a little bit faster just because you can pick smaller structs, but that doesn't mean that you can shave off that much. A good solution, one of the solutions is to have a decentralized state. You don't always care about having a global single state. Sometimes you can just have local states that you update in your own process, in your own part of the job, and every now and then you can acquire those states, acquire the global one, and update everything. Or sometimes you don't even care. For example, if you have many users, you can shard your users in different services and have a reverse proxy that says, okay, this user, I'll send it to that shard, and basically never care, because maybe users don't interact that much. And this is doable, but you have some requirements. So you need to know that roughly every task will take a reasonable amount of time, and that your queues are stable, because if one of those channels fills up too much, in this architecture, you cannot steal a job. You cannot say, okay, I'm full, it's your job to do the rest. So make sure that more or less you can do this actual work in parallel. One other solution, which is the most broadly adopted one, is to batch updates. So if you have your central state, you know you're going to update it basically at every loop. Just batch the instruction that you're going to execute, put them together, put them in a slice of stuff to do, and push them to the channel. You're going to acquire the channel much less, and that is good enough. One thing is that this gives you eventual consistency, not consistency. So if you're like a bank, you might not want to use this solution because you can spend money twice. I mean, depends on what your threat model is, but let's say that this might not be always the best solution, but it's one that scales pretty well. Now, one thing is be aware that every time you you break something apart, you split it in pieces, you will have to still have a mutex. It's just you acquire it much less frequently. And if you do that, you might want to check how your shards are done, because I've seen people just saying, okay, my library is actually a hash map that has strings as keys, so I'm going to split by the alphabet. So I take the first letter. If it is A, I will just acquire the bucket of A's, and that just divides the contention by 24, or 26, or depending on your alphabet, several thousands of glyphs. But that kind of seems to work in theory, but then I've seen that cache being used for websites. And more than 80% started with www. So they were always acquiring the same lock on the W. I mean, yes, they sharded and they obtained absolutely nothing except for making their code more complex. So every time you optimize, be aware of your data. You should always keep your data structures in mind. If you are writing a general purpose library and you want that to make that concurrent, safe, and very fast, you're going to have a hard time getting it right. This principle is called the zip flaw. I suggest you not to read about it, just be aware it exists. But there are links in the slides. So when you use mutexes, you have one more trick that you can use. If you know you have many more reads than writes, you can use a read-write mutex. Don't use it everywhere because it's slower than the actual mutex. So if your reads and writes are roughly the same amount, don't just throw a read-write mutex in it. It doesn't make sense. And I've seen this as a common pattern. It's not always faster. It's only faster if it means something. And one thing that I really suggest not to do is trying to go faster than a mutex. If you go lock-free, I'll let you know that mutexes in Go are already lock-free. This is the entire code that executes in your machine when you acquire or release a mutex, if it's not contended. It's this. You just have an atomic compare and swap and atomic add. If you try to go faster than that, good luck. I'm not saying it's impossible. I'm pretty sure that someone can come up with some clever idea to abuse some hardware, poor hardware, and make it faster. But for the general case, I suggest not to. I've seen people using atomic operation on 64 bits. Prometheus was the case, and they realized that on ARM those are not granted to be atomic. So 32 bits were written in one moment and 32 bits in the other one, and that must have been a fun debug session. I love this kind of debug session. So up until now, we were in the so-called safe zone. I hope that everyone was pretty much able to understand the reasoning behind those things. Now we abandon logic. Logic is not fun to deal with. I mean, it just works. So I'm going to give you an example. I wrote this code. It's generic. Don't get scared. Where type was a different type. Those are the three types that I use. So you int 8, you int 32, and you int 64. So just imagine to replace these three types in this position once per program. And then I run this program on this laptop. My question is, which version is faster? This program does, for as many cores as I have, it increments a variable in a slice. So I create a slice with 4 slots. I have 4 cores, and I spawn 4 Go routines. Each one is going to update its own slot. So no locks, no everything. They access different memory zones. Which one would you say is faster? The one that writes 8 bits, 32, or 64? Remember that the 64-bit one, writes like way more data than the first one. Who says the 8-bit version is faster? Okay, 32 bits, 64. Okay, it is way faster to write more bits. And I was looking at this result in this benchmark, and I went back to the benchmark, and I was like, okay, what did I get wrong? What can I fix to make this make sense? It actually made sense because I was working on a real machine, not a virtual one. And if you have to deal with real machines, you have to keep this in mind. Basically, every time you access memory, you're going to hit some kind of latency. If you access a register, you're going to go very fast, and registers are inside cores. But every time you miss a cache, you need to go one level up. And if you hit the main memory up there, you're wasting thousands of operations just waiting for the memory to be there. Modern processors try to speculate on some things, and as we've seen, turns out to not be that great of an idea. But I wouldn't count too much on that. So in this case, this is what is called false sharing. I was still acquiring some sort of mutex underneath, because I needed to write to a slice that was too small. So every time I updated a bit of that locally, I needed to hit upper level of caches to tell the other cores, hey, I updated this line, because my default line size is 64 bits, and I can't write less than that in an atomic way. To solve this, Go provides you interesting ways. In a struct, you can have underscore declaration. That underscore means that variable can't be read, can't be written without reflection. Don't do reflection on underscores, please. And if you compare those structs with an equal, they're going to behave as those underscores didn't exist. So even if you set those with the reflection, they're going to compare fine. This is why it allows you to have cache lines not contended, even if you just write in a little bit of it. The alternative, if you have a slice, you can pad it. Just do your computation in parallel with some padding in between, and before you return, just defrag your slice. Don't return padded slices. That's a horrible API to have to deal with. At this point, one might think, okay, but what if I just need to read? I mean, I just acquire a read lock. Most of the time, I'm just going to read, so I don't care, because I'm not going to write, and caches don't need to get updated. I'm going just to hit the cache every time. Or so you would wish, because it's not that way. So when you acquire a read lock, you need to update it and tell the system that there is one more reader. So you update a counter, and that hits the topmost level of cache of everyone that is sharing the mutex. So every time you acquire a read lock, you actually perform a write. And that can get you slower, because basically it's everything you needed to do. In my example, I just need to increment, to read an integer value. And to do that, I was writing an integer value, which is suboptimal. Let's put it this way. To address this, well, there is no good way to address this. There are some hacks that you can use. There are some libraries that are in the standard libraries that help you with that. But this is very hard if that data is going to change at some point in time. You have to have some concept of generation and switch to the next generation. It's hard. I suggest to not implement this by hand. Go for a walk, do some sport. It's fine. Buy more hardware. You can afford that. One helper that you can use is Syncmap. Syncmap is not, as many think, just a hash map that behaves well with concurrency. It's a very specialized data structure. Don't overuse it. A Syncmap is a complex data structure that makes sure that if you read way more frequently your data, then you write it, and you can assume that you don't need a snapshot, a coherent snapshot of that map, you're behaving better towards the caches. But just give you a little bit of concept of this complexity. Syncmap methods receive pointers to struct with an atomic value that points to a struct, with a map that points to a map header that points to a hash table, whose elements are themselves pointer to atomic pointers to interface values that are pointers that point to concrete values which may themselves be pointer. You can use this, but make sure you just do that when you need it. And this makes you faster, and it was actually a pretty good improvement for maps that you initialize at init time and never write again, for example. Or like you change configuration every now and then it's fine to acquire a lock or just distribute your workload, then it's fine, you can use that. But it kind of loses type safety because you have to use an anti-interface everywhere. So if you do this, if you use this map, write type safe wrapper. So for the getters and the setters, type them until we get generics in Go. If we get generics in Go, I suggest to write a tiny wrapper of like 6 lines that makes sure that you're using the same type everywhere for keys and values. But at this point, what if you need something that is not a map? What if you need to read more frequently than you write, and you can't really express that as a map? In that case, you might want to use atomics, but you're going towards a whole lot of pain. Atomics make use unsafe if you have to store struct. And if you write unsafe Go, you might as well write C. I don't know. The point is, no, it's still better to write Go because it gives you a lot of safety in the rest, but these kind of things don't work well with, for example, the runtime, because if you use atomics in this way, the runtime is just going to give up on some things. For example, the race detector. Who knows about the race detector? Good, good. So you're used to rely on the fact that if you compile with -race and a race manifests, usually you get a panic for that. If you use atomics, what the runtime is going to say is, okay, there is an atomic here, I suppose you meant a memory barrier of some sort, then you access global state, fine, do whatever you need, and there is a race, you probably intended that, I mean, you're using atomics, you probably know what you're doing, and the race detector is not going to detect anything, so you're pretty much alone. And also, this is hard code to write. I wrote some kind of code. There is a lot of lock-free code in the Go runtime. I suggest to read it as a learning experience. Makes you feel like you need to learn more. And then after a long read, you realize you didn't really want to learn that much. It's very insightful, and I think that the Go runtime and scheduler is one of the most beautiful pieces of software that I've seen with regard to locks and contention and concurrency, but I wouldn't ever try in my life to write something like that. There are some simple patterns that you can use. So for example, if you just need read and very rarely write, you can read with atomic load. There is going to be a type after the load, so load int 64, load whatever. And when you need to store, you need to write that loop. This loop basically loads the value, does the increment or changes the variable as needed, and then it tries, compares and swap with the old value and tries to say, okay, if this is still the old value, let's try to swap it atomically. If it's not, you have to retry. So you reload and you do the thing again. As you might guess, this is a spinning loop. So if you end up using it too much, the runtime, at least until Go 113, is going to stop, and you're going to take over everything. And if a garbage collection is needed at that point in time, your software is going to go down. So you use this carefully. Just make sure you don't collide with other writes too much. And just as a little bit of history that I wanted to add, at one point, Go did this amazing refactor of moving to concurrent basically everything. And everything now runs in a very organized way, but without locking too much or without too much central state. And a couple of bugs emerged. This happened in 2011, and one of the best bugs that they found was the first one that says, these cause some random-looking memory corruption. If you write a memory-safe language, you don't expect this kind of bug to emerge. And even the other one, another one that I saw is the wait group would just wake up at some point, but it wasn't meant to. And if you write your code expecting your wait group to be reliable, that kind of can do weird things. At the time, the runtime was still written in C. Sorry about that. And this was the culprit of the bug. And I was so amazed by the fact that those 4 lines could break so many things and cause memory corruption. And before I went to see what fixed the bug, I did a little game that I invite you to do. I was reading them, and I said, okay, I want to find a race. I know there is a race condition, and I tried to look for it. So this is atomic add. So this was just doing some things, and at one point it said, okay, atomic add 1, and if this is equal to this thing minus 1, then wake up. This seemed so simple, and I was like, why, how did that get wrong? And when I saw the fix, I was puzzled, because they stored the nproc before, and then they did the atomic add. The reason for that is that when they were doing this comparison, that value might have changed. And even the original one might have changed. Because when you do atomics, you have no concept of this is still the value. Every time you look at something, it changes. It's philosophically beautiful. I wouldn't suggest to push it to prod. And a little bit of a recap. To measure your stuff, pprof trace, you will find out that most of the time locks are not a problem. Fix the other stuff, and then you'll find out locks might be a problem. And then you go in deep and try to either shard your state, batch your updates, or do some paddings if it is a false sharing case. And in any case, every time you do this, measure again. Don't just say, okay, I applied this thing, I sharded the state, so this is probably going to go faster, and just push it, because that doesn't work. I've seen people introducing caching or introducing some advanced algorithm in their code and realizing they were going slower. So do comparative benchmarks and measure many times. One more thing, if you measure on a laptop or on an Intel processor, you will realize that it goes on turbo in the first benchmark you do, and then it overheats, then it goes back to normal execution. So the first benchmark is always going to be faster. So don't do that on an Intel processor unless you really want to get weird results, which I got. And there are tools to reduce this kind of effect, and there is a very nice talk by Daniel Marty about measuring. I suggest to take a look at it. And this was my talk. So if there is any questions or any complaint, I'm open to complaints. Okay, then I have a question for you. How many of you have used read-write mutex in their code? Wow. Okay. Syncmap? Sync pool? You don't count. Okay, that was interesting. Thank you.